Welcome to this lecture in the ongoing series of lectures in real analysis. Today we are starting a new module on sequences, and let us briefly recall what we did the last time. So we showed that we discussed what is the square root of a real number, and then we showed that every non-negative real number has a unique non-negative square root. Here I have written positive real number, that doesn't matter. And we also found that there do indeed exist irrational numbers, because since root 2 is irrational, root 2 is already known to be not rational and it exists, so it has to be irrational. Basically, this set is non-empty. And the first exercise asks you to show is that the set of irrationals is actually dense. It is much more than non-empty. Alright, and these are the rest of the two exercises, so please pause the video and solve them. And now let us go to the material of this lecture. So I have something to get out of the way before we proceed. I could have done this in the next lecture also, but let me just do it now because it's a very simple definition that we have been avoiding so far. So this is basically the recollection of absolute value function from high school. So define a function, or rather the function, or maybe it's better to say a function. Define a function which consumes a real number and produces a non-negative real number. So let me emphasize, what is this? This is all real numbers which are non-negative. So how is this function defined? It consumes a real number and produces the same real number if the number is non-negative, and minus x if the number is negative. So this is the absolute value. This is called the absolute value of x. So how do I say that? This is the absolute value of x. Just a definition. And one must have seen the graph of this function definitely in high school, which is as follows. So here we have, so this is the x-axis, this is the y-axis, which is too big. This is the y-axis, and the graph looks like this. So there is this pointy thing at the origin, and this you must have seen this before. And let me remark that one may think of the absolute value of x minus y, which is also read as, or at least I read it as, mod of x minus y. So I sometimes read this as mod, and I hope that is not confusing. Modulus, perhaps it comes from there. Anyway, so one may think of absolute value of x minus y as the distance between x and y, and pictorially, if this is the real line and we have 2 points x and y, then this length is what one should think of as x minus y absolute value. Okay, one very important thing to note is that this inequality holds for all real numbers, and this is called the triangle inequality. So this is the triangle inequality. Very easy to prove, so I leave this as an exercise. And let us also note that a subset A of R is bounded if and only if there is some real number. There is some, well, I could say any real number, but let me just emphasize that it's a non-negative real number such that mod of x is less than equal to k for all x in A. I'm not saying anything profound. Here you have the real line, and let's say this blue part is A. Just I've arbitrarily shaded something, and let's say here we have the origin, maybe it's here. So just find some k such that k is bigger than anything that is positive in A, and minus k is lesser than anything that is negative in A, and then you'll have this. So anyway, just justify this for yourself. Very simple. And recall that what is meant by a bounded subset. A bounded subset is just a subset which has an upper bound and a lower bound. That's what a bounded subset is. So it's a very simple fact that I stated, and I hope this much is clear. And now let us go to the topic of today's lecture. So what is a sequence? So let us first give an informal definition. So let X be any set. So we are going to define a sequence in X. So a sequence in X, informally speaking, meaning not very precisely speaking, is anything of the form x1, x2, x3, where each xi is an x. So it's just, it looks like a sequence. That's what a sequence is, but let me make it formal. So what is the problem with this? It seems like it's well defined. What is the problem with this? The problem is there is no formal mathematical object which allows you to, a priori at least, write things like x1, x2, x3, ... What does that even mean? Mathematics as we write in the modern standard way has objects which are defined via sets, functions and relations, and compound objects built out of them. There is no such object as it is in the standard formalies. So let's try to express this concept, whatever it is trying to capture, in terms of functions or relations or whatever, but we can do, functions are enough to express this. You don't need to go to relations. So formally, the proper definition of a sequence, though somewhat less colloquial or looks a little bit more contrived than it has to be, a sequence in X is a map from the naturals to X. Just any such map is a sequence. So we need to reconcile the definition, this formal definition, with the more intuitive informal definition. Basically, given such a function, to that function we can associate, so given f, define or write xi as xi to denote f of I, the image of I under f. And then we may just write this x1, x2, x3 ... to mean f, because it really captures the same data as f is capturing. Right, from here you can easily recover f, and from f you can recover this kind of data. So that's that. And in fact, there is a more compact way to write this. So we may also write this to denote f, or simply to denote f, when no confusion can arise. This is the most proper way to, if you really want to think of a sequence like this, and this is how we will think of sequences. This is the most proper way to denote a sequence. And but this gets cumbersome every time writing from where to where you are running the n. We just don't do it. We just write like this. And also note that some authors do not use this symbol, they use a curly braces. I do not like that because then it looks like a set. A sequence is not a set. A sequence in X is not just some subset of X. It matters how this thing is not the same as x2, x1, x3 because the function it denotes is different. So do not confuse a sequence with a subset. Okay, and let us just see a very simple example. So just let little x be fixed arbitrarily. Define as f of n f of n equals x for all n. Then this is a legitimate sequence. It takes the same point at every natural number and it is a legitimate sequence. And in this the more likable picture, we will denote f by x. It looks a bit weird, but this is how you may denote this sequence, the constant sequence, if you will. Okay, so this is just an example, but what we will really be interested in is real sequences, meaning sequence which where your set x is the set of real numbers. So those sequences. So let me just say that a sequence xn in R. Yeah, so okay, I am not going to say that. Basically, we know what is meant by a real sequence because I have defined the notion of a sequence in any set. So now when I say a real sequence, I just mean each of these xn's are real numbers. So now suppose we have a sequence in R, then we say, or rather, sorry, a sequence in R is said to be bounded if the corresponding set is a bounded subset of R. So meaning the values this sequence takes is contained in a bounded set. That's what it means. So the most natural definition of a bounded sequence. And let me just note that this is bounded if and only if there exists some real number which I call non-negative, such that this happens for all natural numbers. So again, just like we noticed for bounded sets, a set is bounded if and only if this kind of thing happened, as we mentioned in the section on absolute values. So I'm just repeating that in this special case where your subset of the real numbers is indexed by natural numbers. So I just wanted to note this very, very simple fact. Okay, and now let's see some examples. So define let xn equals 1 by n for all n. So the sequence now that we get out of this is bounded. Clearly, because 1 is an upper bound and 0 is a lower bound. So it's a bounded sequence. Okay, And let's see an unbounded sequence. So yeah, unbounded, when we have defined a bounded sequence, we have also defined an unbounded sequence. An unbounded sequence is a sequence which is not bounded. Okay, so let xn equals n for all n, then the sequence xn is unbounded. It does not have a bound. And here is an exercise for you, which says that let xn and yn be bounded sequences. In R, of course. Then show that the sequences that you get by adding corresponding terms and multiplying corresponding terms are also bounded. Right, so the quote unquote sum sequence and the product sequence that you get of any two bounded sequences is also bounded. Again, very simple exercise, so I'll leave it to you. And now for the very important concept of a subsequence. Okay, so let X be any set. And we have a sequence in it. Okay, so we say that a sequence yk, k from 1 to infinity. So I'm not using the same letter n here, I'm using a different letter, is a subsequence of the given sequence if there exist n1 less than n2 less than n3 such that yk equals xn sub k. So there are two subscripts. This is a single number which happens for all k. Alright, so that's the definition of a subsequence, and I hope it is clear why this prefix sub is used. So we have x1, then we have x2, x3, x4, and so on. A subsequence basically picks out some of these guys. It may leave out whichever, but it picks out just whichever it likes. So that's basically a subsequence. So if you decode what this is trying to say, you will understand my comment. Okay, and we denote, so once these n1, n2, n3 are found, we denote this sequence as this. So this time it is important to use these decorations, because if I don't do this, then you may get confused as to what's happening. There are two variables here, so what to do. But it's also understood, as when we learn more and more, we actually do drop them because it is clear from the context what this means. Okay, so we will denote that thing simply as x n sub k and put a bracket here and hope that it is understood what this means. But this is, I would say, the most proper way to write it. Okay, so that's it. But let us also look at the notion of subsequences from the picture of functions. So suppose we have a sequence. So if f is a sequence in x, then a subsequence of f is a function let me call it g from n to x such that there is a strictly increasing function phi from n to n, which makes the following diagram commute. So I'll explain what that means. So here we have n, this is my sequence, this is phi, and this is the something that is supposed to be a subsequence. Okay, so a lot of things have been written. This we have defined subsequence in an alternate way, although it's the same definition and we need to reconcile the two definitions. So but right now just focus on this. So we have been given a sequence. And I'm saying that another sequence is a subsequence of f if there exists a strictly increasing function. So what do I mean by strictly increasing function? So let me define that here. Phi n to n is called strictly increasing if phi m less than phi n whenever m is less than n. So that's the definition of strictly increasing. Okay. Right. So okay, so fine. Once we have a phi, let me write ni to denote the image of phi. I mean image of I under phi. So the strict increasingness of phi says what? It says precisely that this is the case. Okay. And then what is g of anything? Let's say g of k. G of k is, yeah, so I did not say what the hell is this. So when I make this diagram and say that it commutes, it just means that starting from any vertex, meaning this kind of thing, you can take whichever path you like. So the paths are allowed only to go in the direction of the arrows. You can't go against the arrows. So let's say we start from here, then there are two ways we can go to this destination. One is this way and the other is this way, and these two things should give the same answer. That's what it means to commute. Now if you start with this destination, there is only one way to go to this destination, if you start with this source, then you can't go here. There is no path which gets you here. So there is only one path, and it goes from here to here. So there is nothing, no conflict here anyway. The only interesting thing happens from when you choose this source and that destination. So you can go this way or that way, and the two things should be equal. So suppose I pick k here and I go that way, then I end up with g of k. But if I go that way, what do I get? I get f of phi of k, because once I start with a k, it becomes phi k when I reach here, and it becomes f of phi of k when I reach there. So that's equal to that, but which is equal to phi of nk, because we have just defined that to be equal to that. It's just a change of notation, really. So you see where this is going. Basically, instead of g of k, if I write y sub k, and instead of f of n, I write xn, then I see that these two things are equal, and this is exactly what we did in this whole business. So something to keep in mind. I mean, maybe we'll never use this, but I wouldn't sleep peacefully without discussing this. So yeah, I think this is all. That's what a subsequence is. Okay, I'm done. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.